In this video, we're going to look at the Unit 7 end of unit review for geometry. Number 1 gives us an inscribed angle BAD at 30 degrees, which we can see in this picture right here. So BAD is this angle, and it asks us to find the measure of the central angle. So here's the inscribed angle that they gave us, and here's the central angle that they're looking for. So remember, when we have an inscribed angle, that's where the vertice or the vertex is on the edge of the circle, and the angle opens to this intercepted arc. So this intercepted arc is 2 times as big as this angle measure. So when we multiply 30 by 2, we're going to get this intercepted arc. And then the intercepted arc and the central angle are equal to each other in size. So that's going to be 60 degrees as well. So the central angle is 60 degrees. And then the measure from the arc from B to D not passing through A is that 60 degrees. And then the measure of the arc that does pass through A, so if we go the other way from B to D, so go around this way, we know a circle totals 360. So if we do 360 minus the 60 degrees of this smaller arc BD, we would get 300 degrees for the arc from B to D passing through A. Number 2 gives us a few different problems. A says angle BAC is highlighted on the diagram below. In a different color, highlight the angle congruent to that. So again, this is an inscribed angle since the vertex is on the edge of the circle. So we know that it opens to this intercepted arc. And then we see that this other angle, CDB, is also intercepting this same arc. So it starts at C, goes to the edge of the circle, and then goes back to B. So since these two angles share the same intercepted arc, that means that they are congruent to each other. So this angle here would also be 38 degrees, just like the highlighted one. B, the arc from B to C not through A is highlighted. What is the measure of this arc? So that's the same as this green arc over in this problem. And that arc is going to be 2 times the measure of the inscribed angle. So we see this inscribed angle here is 38 degrees. So then we'll be able to multiply that 38 degrees times 2, and we'll get 76 degrees for the measure of this arc. Part C gives us that segment AD and BD are tangent to the circle. So tangent means that they hit an exactly 1 point. And so that point we can see from this first one is A. And then we know that when we have a tangent line that touches a radius, that creates a 90-degree angle. So we know that this is 90 degrees since that's where the tangent line touches this radius AO. And then if we do the same thing on the other tangent line, so we see this tangent line hits at B and OB is a radius. So then that means that this angle here is also 90 degrees. Then we know that the total degrees in a quadrilateral, so if you see we've got this quadrilateral here, so the total degrees in any quadrilateral is 360. So we can do 360 minus 90 minus 90 minus 65 to get our leftover angle here of 115 degrees. So that's going to be the measure of that central angle, AOB. Number 3, 2 quadrilaterals are pictured. Is either quadrilateral a cyclic quadrilateral? Explain or show your reasoning. So cyclic quadrilaterals mean that they can be inscribed within a circle. And we know that that the property that will tell us that when we're given angles is that opposite angles need to add to 180 degrees. If that happens, then we know that the quadrilateral can in fact be inscribed into a circle. So opposite angles are going to be ones across from each other. So this 120 plus 60 is equal to 180. So there's one set of opposite angles that are equal. And then the other set here is 30 and 150. And 30 plus 150 equals 180. So this first quadrilateral A, is definitely cyclic. So then let's check out quadrilateral B. We see 120 here, and the one across from that, or not next to it, is 30. 120 plus 30 does not equal 180. So automatically, this one is not cyclic. That means that quadrilateral A is the only cyclic one, and that's because the opposite angles add to 180, as shown here. Number 4, construct a circumscribed circle around triangle ABC and DEF. Show at least 2 perpendicular bisectors, the point where they intersect, and draw the circumscribed circle. So you'll need your compass for this, and you'll open to any of the 2 sides that you want to, because you're just going to create a perpendicular bisector of 2 sides. I'm going to open up for this DF. You just need to be open to wider than halfway. And I'm going to make these marks small so we don't get so confused on our drawing. So we're going to do this way. Then I'm going to keep the circle the same size and move it to the next vertex and draw my arcs again. Then where these 2 circles intersect, I'm going to connect that with my ruler or with a straight line. So you can take your ruler and set it there and have it connect the intersection points. So just get it lined up there. Mine doesn't look like it's going to line up super well, so I'm going to try a straight line drawer here and see if that'll work better. So you want it to just go exactly through those 2 intersection points. Then you'd move on to another side. So I'm going to do ED here. And now you can change the size of your compass if you would like. And I'm going to do the same thing. So draw a circle around this one. I don't draw the full circle. I just draw a half circle-ish. And then connect again. You just need to see where they cross. And this is where it can get kind of confusing on your paper when you have a lot of drawings. So you got to try and make sure you can see where these 2 circles are actually connecting. And that's going to be right here. So let me get a little dot drawn in there. And then here, lay your ruler along there again and connect those. Make sure you extend it so you can see where these 2 perpendicular lines cross, or sorry, perpendicular bisectors cross. And then that's the center of your circumscribed circle. So you'll put your compass back on there, and then you will open your compass to any one of the vertices of the triangle, because they should all be the exact same distance away, so it won't matter which one you open it to. And then you draw your circle, and it should hit all 3 vertices. Then you would repeat for this next one. Now on this next one, I'm actually going to just draw the same size circle the whole time and show you how you can do that. So I'm going to open to wider than halfway on the largest side. And then I'm just going to draw 3 circles, 1 around each vertex. And I'm going to keep my circles the same size this time. That way I don't have as many markings. And I can then just show where these 2 intersect, and I'll follow it around and they intersect here and here, then I can connect those. Make sure you get it exactly through that intersection. Then I can find another set of intersections. So I see this one, and if I rotate, kind of follow these circles around, that crosses over here. So then I'll be able to connect these ones as well. And then again, that gives me the circumcenter of the circle. So I will be able to go in and draw the circle, the circumscribed circle. So I'll put my center at that point, open up to one of the vertices, and then draw your circle, and it should hit all three vertices. Mine's off a little bit. That my board just gets a little bit skewed sometimes, but if you do it correctly, it should pretty much hit all of them. Number 5, the image shows two circles, circle A and circle B. Are circle A and circle B similar to each other, and explain your reasoning? And yes, all circles are similar because they only have one measurement to compare. So when you compare their radius, you're going to be able to get a scale factor that will take one to the next. So if we look at 20 and then 4, the scale factor here would just be dividing 4 by 20. So circle A to B, 4 over 20 would be the scale factor, and that would simplify to 1 over 5. Then the circumference of circle A to circle B. So determine the scale factor and the factors of each of these. Circumference is just a linear measurement, so it's going to be the same scale factor as your circles are. So if you just want to copy down the scale factor from this one, that's going to be true. You could also figure out the circumference, and then you could compare them that way. So remember that circumference is 2 times the radius times pi. So the circumference for this one, 2 times 20 is 40 pi. And then 2 times 4 is 8 pi. So then if we compare those, 8 pi over 40 pi, the pi's will cancel. 8 and 40 both divide by 8. 8 divided by 8 is 1. 40 divided by 8 is 5. And you see that it's that same scale factor as when we compared the radii. Then the area factor. So remember, scale factor is k. Your area factor is k squared. So this is just going to be 1 over 5 squared. So the 1 squared is 1, 5 squared is 25. So that's going to be our area factor. Again, you could actually calculate the area. The area is just r squared times pi. So we would take 20 squared, which is 400 pi. And then this one would be 4 squared, which is 16 times pi. And then you could compare those. So 16 pi divided by 400 pi. The pi's will cancel out. 16 divided by 16 is 1. 400 divided by 16 is 25. And you see that you get that. Part C says the central angle in radians. Remember that when you're doing radians, it's just the arc length divided by the angle measure, or sorry, the arc length divided by the radius. So we have in this one, the arc length is 5 pi, and we'll divide by 20. So it's going to be 5 pi divided by 20. 5 and 20 both divide by 5. So we would end up with pi over 4 when we simplify that. And then this next one, the arc length is pi and the radius is 4. So we would do pi divided by 4 for that one. And then we can see that they are the same as each other. Then the last one talks about the ratio of the area of each sector to the whole circle. So this one's a little bit confusing because it says the word area, but that doesn't actually matter because it's just looking at the ratio of this piece to the whole circle. So how much of this compared to the whole circle do we have? And pi over 4 radians, okay, if we remember what a radian is, we can take half the circle, which would be at pi. This is cutting this top part into 4 pieces. So pi over 4 radians is really 1/8 of the circle if we looked at the whole thing. So it's taking this top half pi divided by 4 to get the radian, but then the whole circle we know is 2 pi, so it's actually 1/8 of the whole circle. Number 6, given the circle has a radius of 12 feet and the shaded sector has a central angle of 120 degrees, find the area of the shaded sector. So we can do the sector area formula, which is theta over 360 when we're in degrees, and then times pi times the radius squared. So we're taking the percent of the circle we have times the area formula. So we have 120 degrees here out of 360. And then we have times pi and then times 12 squared. So this is 120 over 360 times 144 pi. And really 120 over 360 is 1/3, but you could certainly just use your calculator to do this as well. But we'd have 1/3 of 144. So if you need to leave this in terms of pi, this would be 48 pi feet squared. Or if your teacher wants you to do it in decimal form, then you can just multiply out pi as a decimal, and you can get 150.8 feet squared. So either one of those is fine, depending on how you need your answer to be. Then we want the measure of the arc that is not highlighted. So we want this arc. So we're going to want this central angle here. So we'd have 360 minus 120, and that's 240. And then arc length is a part of the circumference. So when we do arc length in degrees, we're still going to do the central angle over 360, but now we're multiplying by the circumference formula, 2 times pi times r. So in this case, it would be 240 over 360 times 2 times pi times 12. And 240 over 360 is really 2/3 if we simplify it. And then 2 times 12 is 24 with pi. 24 divided by 3 is 8. 2 times 8 is 16. So our answer in terms of pi is 16 pi feet. Or you could have multiplied that all out in your calculator and gotten a decimal of approximately 50.26 feet. Number 7, a circle of radius 7 is pictured. Find the sector area of the picture shown. So now we're in radians. And so for radians, your arc length formula is going to be your sector area formula is going to be 1/2 times theta times r squared. So we're going to do 1/2 times the angle measure, which is pi over 4. And then times the radius squared. So in this one, we would have 49 times pi on the top because there's like a 1 under here. So 49 times pi on the top and then divided by 8 on the bottom. This would be your exact answer. And then if you're wanting to put it in decimal form, you could just type this into your calculator and you would get about 19.24 centimeters squared. The other thing is you can see that pi over 4 is 1/8 of your circle. And then remember that the area formula is pi times the radius squared. And 7 squared is 49. So 49 pi is our area. That's where that 49 pi over 8 is coming from. 1/8 of the whole thing, so 1/8 of 49 pi. Then what would the area of the sector be if the central angle was enlarged to 3 pi over 4? So instead of pi over 4, we're going to have 3 times pi over 4, because we're going to have 3 pi over 4. So now we would just have 3 times as much. So you could do 49 pi over 8 times 3 if you needed it in exact form. So you'd do 49 times 3, which is 147 pi over 8. Or you could do the 19.24 times 3 and get the decimal version of 57.72 centimeters squared, whichever method you prefer.